Hi there, in this video we are tackling LeetCode problem number 20, valid parentheses. It is an easy level problem, but it is super important for coding interviews and real-world programming. This problem teaches you about stacks and bracket matching, concepts used in many applications from syntax parsing in compilers to evaluating expressions in calculators, validating HTML, XML or JSON, and even powering code editors that highlight unmatched brackets. Mastering this problem gives you a skill that go far beyond LeetCode. So let's dive in and see what needs to be done. Let's start by understanding the problem statement. We are given a string S containing just the characters opening round bracket, closing round bracket, opening curly bracket, closing curly bracket, opening square bracket, and closing square bracket. And we need to determine if the input string is valid. Now, an input string is valid if three conditions are met. First, open brackets must be closed by the same type of brackets. Second, open brackets must be closed in the correct order, meaning that the most recently open bracket must be closed first. And third, every closed bracket has a corresponding opening bracket of the same type. Now let's quickly go over the constraints. The string length can range from 1 to 10,000 characters, and the string consists of parentheses only. These constraints tell us that we need an efficient solution, since we could be dealing with up to 10,000 characters. But the limited character set makes our validation logic straightforward. With those constraints in mind, let's walk through our first example. We are given the string S equals a pair of opening and closing round brackets, and the expected output is true. This is the simplest case. We have one opening round bracket followed immediately by its matching closing round bracket, so the string is valid. Here is our second example. S equals this string, and the output is true. This demonstrates that different types of brackets can coexist in the same string. We have a pair of round brackets, followed by a pair of square brackets, followed by a pair of curly brackets. Since each opening bracket is properly closed by its matching type and in the correct order, meaning the most recently opened bracket of a given type is closed first. Therefore, the entire string is valid. Let's look at our third example to understand what makes a string invalid. So S equals this string, and the output is false. Here we see a critical violation. There is an opening round bracket followed by a closing square bracket. This breaks our first rule, which states that an opening bracket must be closed by the same type of bracket. The opening round bracket should be closed by a closing round bracket, not a closing square bracket. Now, our fourth example shows a more complex valid case. So S equals this string, and the output is true. This demonstrates nested brackets working correctly. We have an outer pair of round brackets, and inside them we have a pair of square brackets. The square brackets are properly closed first, then the parentheses are closed, maintaining the correct order. Finally, let's examine our fifth example. So S equals this string, and the output is false. This is a perfect example of incorrect ordering. Although we have matching pairs, one set of round brackets and one set of square brackets, they are not properly nested. The opening sequence is first an opening round bracket, then an opening square bracket. But the closing sequence is first a closing round bracket, then a closing square bracket. This violates the correct order rule. The most recently opened bracket must be closed first. So here, the square bracket should close before the round bracket closes. So now that we have seen the examples, let's dive into the solution approaches. We will explore two main methods. First, the brute force pair elimination approach, which repeatedly removes matching pairs. And second, the more efficient bracket validation approach using a stack data structure. Let's begin with the pair elimination approach. This method works by continuously searching for adjacent matching bracket pairs and removing them until no more pairs can be found. If we end up with an empty string, the original string was valid. If any brackets remain, the string was invalid. Let's visualize this process with the example string S. We start by identifying the innermost matching pairs. In this case, we can see square brackets appear 3 times as adjacent matching pairs. We remove all occurrences of these adjacent square brackets, which transforms our string to this. Now we look for the next set of matching pairs. We can identify 1 round bracket and 2 curly brackets as adjacent pairs. Removing them leaves us with just a single pair of round brackets. Finally, we remove the last adjacent matching pair of round brackets, which leaves us with an empty string. Since our string is now empty, we can conclude that the original string S was valid. Simple, right? For the code implementation of this solution, we begin by defining the method signature. The method is called isValid, which takes a string S as its parameter and returns a boolean indicating whether the string is valid. Now, the core logic for this approach is a while loop that continues as long as there is at least one valid pair in the string. The loop condition checks if the string contains any of the 3 matching pairs. Inside the while loop, we systematically remove all occurrences of each matching pair. First, we remove all occurrences of round brackets from the string. Then we remove all occurrences of square brackets. And finally, we remove all occurrences of curly brackets. After these 3 replacement operations, some innermost pairs may have been removed, exposing new adjacent pairs. So, the while condition checks again if there are any remaining pairs that can be removed. This process continues until no more matching pairs can be found. Finally, we return the result by checking if the string is empty. If all brackets were successfully removed, the string will be empty and we return true. Otherwise, some unmatched brackets remain and we return false. As for the time complexity, in the worst case, we might need to perform multiple passes through the string, and each pass involves string replacement operations. This gives us big O of n squared time complexity, where n is the length of the string. The space complexity is big O of n due to the string operations that create new string instances. So, while the previous approach works correctly, it is not the most efficient. So let's now explore the bracket validation approach using a stack, which is more efficient and widely used in coding interviews. But before that, let's understand why a stack is ideal data structure for this problem. Suppose we start with an empty string S. First, we add an opening square bracket, then an opening curly bracket, and then an opening round bracket. To make this a string valid according to our problem statement, we must follow the correct order rule, which states that the most recently opened bracket must be closed first. This means we cannot close the opening curly bracket before closing the last opened round bracket. The round bracket must be closed first, then the curly bracket, and finally the square bracket can be closed. This demonstrates why a stack is perfect for this problem. It follows the last in first out or LeetCode principle, ensuring that the most recently opened bracket is the first to be closed. So, the idea is very simple. Whenever we encounter an opening bracket, we push its corresponding closing bracket onto the stack. When a closing bracket appears, we check if it matches the one on top of the stack. If it does not, or if the stack is empty, the string is invalid. Finally, if the stack is empty after processing the entire string, it means all brackets have been correctly matched. So let's visualize the entire process using this example string S. We will go through each character step by step and observe how the stack changes as we process the input. So we start with an empty stack, and we will also use a pointer I to traverse the string. So, at index 0, the first character is an opening bracket. Since it is an opening bracket, we push its corresponding closing bracket onto our stack. We do this so that when we encounter a closing bracket later, we can easily check if it matches the one on top of the stack. At index 1, we encounter another opening bracket, so we push its corresponding closing bracket onto the stack as well. At index 2, we find yet another opening bracket, so we push its corresponding closing bracket onto the stack. Now, at index 3, things get a bit interesting. We encounter our first closing bracket. So the first thing we do is check if the stack is empty, because if it were, it would mean there is no corresponding opening bracket and the expression would be invalid. Since the stack is not empty, we pop the top element and verify whether it matches the current closing bracket. In this case, it does match, which means the popped closing bracket corresponds directly to this closing bracket. So, the pair is valid and we continue processing. At index 4, we find another closing bracket. So we follow the same steps as before. First, we check if the stack is empty, which is not the case here. Then we pop the top element from the stack and verify that it matches the current closing bracket. Since it does, this means the pair is valid and we continue processing. At index 5, we encounter an opening bracket, so we push its corresponding closing bracket onto the stack. At index 6, we find another opening bracket, so we push its corresponding closing bracket onto the stack. At index 7, we encounter a closing bracket, so we pop the top element from the stack and verify it matches the current closing bracket. It does, so we continue. At index 8, we find another closing bracket, so we pop the top element from the stack and verify it matches the current closing bracket. It does, so we continue. At index 9, we encounter a closing bracket, so again, we pop the top element from the stack and verify it matches the current closing bracket. It does, leaving our stack empty. At index 10, we find an opening bracket, so we push its corresponding closing bracket onto the now empty stack. At index 11, we encounter another opening bracket, so we push its corresponding closing bracket onto the stack. At index 12, we find a closing bracket, so we pop the top element from the stack and verify it matches the current closing bracket. It does, so we continue for the last time. At index 13, we encounter the final closing bracket, so we pop the top element from the stack and verify it matches the current closing bracket. It does, leaving the stack empty at the end. So after processing all characters, our stack is empty, which means all opening brackets were properly matched with their corresponding closing brackets in the correct order. Therefore, the string is valid and we return true. But let's say that instead of a closing curly bracket at the end of the string, we had one more opening curly bracket. Since it is an opening bracket, we would push its corresponding closing bracket onto the stack and finish the traversal. In that case, our stack would be left non-empty, indicating that the given string is not valid. Another situation where the string can be invalid, as we discussed earlier, is when the current closing bracket does not match the expected closing bracket when we pop an element from the stack. In both of these cases, we would return false. For the code implementation of this solution, we begin by defining the same method signature as before. First, we initialize a stack of characters to keep track of the expected closing brackets. Now, we start a for loop to iterate through each character in the input string. Inside the loop, we check if the current character is an opening bracket. If it is, we push its corresponding closing bracket onto the stack. Now, if the current character is not an opening bracket, we enter the else block, which handles closing brackets. In this block, we first check if the stack is empty. If it is, it means there is a closing bracket without a matching opening one, so we can immediately return false. Now, if the stack is not empty, we pop the top character and check if it matches the current character. If it does not match, it means we have a mismatched pair, so we return false. Now, after the for loop finishes, we perform one final check. If the stack is empty, it means all opening brackets have been correctly matched with their closing brackets, so we return true. Otherwise, it means there are unmatched opening brackets left on the stack, and we return false. As for the time complexity, this solution runs in big O of n time, where n is the length of the string, since we process each character exactly once. The space complexity is big O of n in the worst case, when all characters are opening brackets and are stored in the stack. So, to summarize, we looked at two approaches: pair elimination, which is simple but less efficient, and the stack-based method, which runs in big O of n time and is the preferred solution for interviews. This problem is a great way to master stacks and the LeetCode principle. And with that, let's wrap up this lecture here, and I will see you in the next one.